March is Women's History Month, and there are women at NASA contributing every day to the success of our current missions and paving the way for future generations to reach for the stars. Mallory Jennings is the first female system manager for the Extravehicular Mobility Unit, or EMU. The EMU is the spacesuit worn by astronauts during a spacewalk outside the International Space Station. Mallory coordinates all the engineering aspects, from hardware to new technologies. From communications to thermal protection to oxygen, all the systems work together to protect astronauts from the harsh environment of space. NASA is designing new spacesuits to use for Artemis missions to the moon. Leanna Rodrigues is leading the team using new technologies to develop and build the Exploration EMU spacesuit. She's the inspirational leader who will help our next moonwalkers. They will have more natural mobility and a robust life support system to explore the lunar surface and beyond. Have you ever driven a remote control car? Now, imagine it was on another planet. Farah Alibay is a systems engineer working on our new Mars rover, Perseverance. As the rover moves across the red planet, the systems she worked on make sure the rover knows the direction it's pointed and updates that position for teams back on Earth. She spent last summer testing our new rover's capabilities in a giant sandbox with a replica of the rover. Not only do we study other worlds, we also study Earth, our very own planet. From space, the Landsat program maps Earth's surface to provide information about our resources and environment. Melody Jam is leading the development of an instrument on the newest Landsat spacecraft that will launch this September. That instrument will measure the surface temperatures of our planet. Lola Fatinyimbo Age uses satellite data and imagery to study forests. Her research reveals how our ecology has changed over time and works to predict how it might change in the future. Lola is working to make our planet a better place. Erica Alston inspires students through the Space Grant Program. She expands opportunities for young Americans to understand and participate in our space projects, just like she did. Erica is a role model for future generations. Did you know the skills used to build spacecraft were also used to develop ventilators for COVID-19 patients? Michelle Easter is an expert in mechatronics, which is the design, assembly, and test of mechanisms controlled by electronics. She was part of the team that designed low-cost ventilators in response to the pandemic. Michelle was the first female to join the mechatronics group at our Jet Propulsion Laboratory. Lori Grindle is responsible for flight programs and projects at our Armstrong Flight Research Center. Lori oversees cutting-edge aerospace concepts and technologies, including experimental aircraft and unmanned aircraft systems. Flight research and testing is vital in the development of new aircraft. Women's contributions at NASA reach other solar systems. Nicole Cologne's work involves the discovery and characterization of exoplanets. These are planets that orbit around other stars. Using several NASA observatories, she was able to study a puffy exoplanet with low density, similar to styrofoam. Nicole's work is expanding what we know about the universe. At NASA, women innovate, break barriers, and explore the unknown. The list of their accomplishments is being built upon every single day. This March, take a moment to recognize the contributions of women in the world around us, and together we celebrate Women's History Month. March is Women's History Month, and there are women at NASA contributing every day to the success of our current missions and paving the way for future generations to reach for the stars. Mallory Jennings is the first female system manager for the Extravehicular Mobility Unit, or EMU. The EMU is the spacesuit worn by astronauts during a spacewalk outside the International Space Station. Mallory coordinates all the engineering aspects from hardware to new technologies. From communications to thermal protection to oxygen, all the systems work together to protect astronauts from the harsh environment of space. NASA is designing new spacesuits to use for Artemis missions to the moon. Leanna Rodrigues is leading the team using new technologies to develop and build the Exploration EMU spacesuit. She's the inspirational leader who will help our next moonwalkers. They will have more natural mobility and a robust life support system to explore the lunar surface and beyond. Have you ever driven a remote control car? Now, imagine it was on another planet. Farah Alibay is a systems engineer working on our new Mars rover, Perseverance. As the rover moves across the red planet, the systems she worked on make sure the rover knows the direction it's pointed and updates that position for teams back on Earth. She spent last summer testing our new rover's capabilities in a giant sandbox with a replica of the rover. Not only do we study other worlds, we also study Earth, our very own planet. From space, the Landsat program maps Earth's surface to provide information about our resources and environment. Melody Jam is leading the development of an instrument on the newest Landsat spacecraft that will launch this September. That instrument will measure the surface temperatures of our planet. Lola Fatinyimbo Age uses satellite data and imagery to study forests. Her research reveals how our ecology has changed over time and works to predict how it might change in the future. Lola is working to make our planet a better place. Erica Alston inspires students through the Space Grant Program. As an engineer, she used our satellite data to focus on air quality and climate change. Now, she expands opportunities for young Americans to understand and participate in our space projects, just like she did. Erica is a role model for future generations. Did you know the skills used to build spacecraft were also used to develop ventilators for COVID-19 patients? Michelle Easter is an expert in mechatronics, which is the design, assembly, and test of mechanisms controlled by electronics. She was part of the team that designed low-cost ventilators in response to the pandemic. Michelle was the first female to join the mechatronics group at our Jet Propulsion Laboratory. Lori Grindle is responsible for flight programs and projects at our Armstrong Flight Research Center. Lori oversees cutting-edge aerospace concepts and technologies, including experimental aircraft and unmanned aircraft systems. Flight research and testing is vital in the development of new aircraft. Women's contributions at NASA reach other solar systems. Nicole Cologne's work involves the discovery and characterization of exoplanets. These are planets that orbit around other stars. Using several NASA observatories, she was able to study a puffy exoplanet with low density, similar to styrofoam. Nicole's work is expanding what we know about the universe. At NASA, women innovate, break barriers, and explore the unknown. The list of their accomplishments is being built upon every single day. This March, take a moment to recognize the contributions of women in the world around us, and together we celebrate Women's History Month.
Artemis systems are ready to fly astronauts, a hot fire test of an Artemis rocket engine, and educating and inspiring the Artemis generation. A few of the stories to tell you about this week at NASA. After extensively reviewing data since last year's successful uncrewed Artemis 1 flight test around the moon and back, NASA has confirmed initial observations that the agency's Space Launch System rocket, Orion spacecraft, and ground systems are ready to fly astronauts on missions to the moon. The agency plans to do just that on Artemis II by sending an astronaut crew around the moon and back. On March 8th, engineers at our Stennis Space Center conducted this year's third hot fire test in the current test series to certify the redesigned RS-25 rocket engines. 4 of the engines will help power our Space Launch System rocket on future Artemis missions to the moon. Second Gentleman Douglas Emhoff, NASA astronaut Yvonne Kegel, and NASA Ames Center Director Eugene Tu joined students and their families at an Oakland, California educational event hosted in honor of Women's History Month. The event featured hands-on STEM activities and NASA items to inspire the students to learn about our Artemis program, which will land the first woman and person of color on the moon. NASA's Imaging X-ray Polarimetry Explorer, or IXPE, captured the light blue color in this new image of a pulsar wind nebula in the constellation Vela. The light blue represents the first ever X-ray polarization data for Vela. The pulsar itself is near the center of the image. Measuring polarization could improve our understanding of how cosmic objects like pulsars accelerate particles to high speeds.
NASA celebrates Women's History Month.
NASA 1, we have an ejection. The aircraft is descending over the North Base area. I have a chute. The pilot's out of the seat and the chute is good. Okay, Bravo, copy.
We had a highly competent team, very experienced, many flights under their belt. We had a number of pilots that flew the airplane. The pilot in particular that was flying that day had been on the program from the very beginning, highly experienced with the X-31.
Each mishap has its own set of circumstances and its own sequence of events. But you find similar issues: communications, complacency, assumptions that haven't been warranted, human frailties. And you have to account for these things in a program.
This is like a chain. You make a chain when you have any of these accidents, a chain of events. Any link of the chain, if it were broken, you would not have an accident.
This was the A-team. We had the best people from every discipline, from every organization, and we lost an airplane. So if it can happen to the best team, it can happen to any team.
The X-31 research effort began in the late 1980s as an international program involving DARPA, the U.S. Navy, Deutsche Aerospace, the German Federal Ministry of Defense, and Rockwell International. The program's goal was to explore the tactical utility of a thrust-vectored aircraft with advanced flight control systems, using an aircraft designed and built specifically for that task.
The X-31 was a real pioneering program. In fact, the X-31 program pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HARV.
The initial X-31 flight tests were conducted at Rockwell's facility in Palmdale, California. But in 1992, NASA and the U.S. Air Force joined the X-31 research team, and the test flight program was moved to the Dryden Flight Research Center on Edwards Air Force Base. And before too long, the X-31 was turning in some extremely impressive results. By any measure, the X-31 was a highly successful program. It regularly flew several flights a day, accumulating over 550 flights during the course of the program, with a superlative safety record. And yet, on the 19th of January 1995, on the very last scheduled flight of the X-31's ship number 1, disaster struck.
This particular flight had been on the books for some time to get done, and it was, by our standards, an absolutely routine flight.
We were not expanding the envelope. We were not trying anything new. We were flying a new pitot-static tube, but this was in a routine mission, a routine task, routine flight environment with an experienced pilot and experienced crew.
But while the flight was routine, there had been some changes to the configuration of the X-31 since its initial flights. In particular, the original pitot tube, which supplies airspeed information to the plane's flight control computers, had been replaced with another kind of pitot tube known as a keel probe. The keel probe gave more accurate airspeed data at high angles of attack, but it was more vulnerable to icing, especially since the keel probe on the X-31 did not have any pitot heat.
We were never to fly the airplane in ice. That was a prohibited maneuver. So if you're prohibited from flying in ice, you don't need a heater.
Normally, the conditions at Edwards are warm and dry enough that icing or pitot heat isn't a concern. But January 19, 1995 was not a normal day.
The unusual part of the day was we had a high humidity at altitude, actually conducive for freezing conditions. And airplane was operated for in and out of some fairly high moisture content for extended periods of time. Led to some indications in the cockpit and the control room that it was causing problems with the air data system.
This particular airplane had a limit to not fly through clouds, through visible moisture. That day, we were flying very close to and occasionally in and out of very thin cirrus cloud. It didn't particularly worry me because everything seemed to be going along quite normally.
But some minutes, like 5, before the airplane went out of control and the pilot jumped out, the pilot observed that there was some moisture around where he was. So he turned the pitot heat switch on. Now clearly when he turned the pitot heat switch on, he expected that the pitot heat would be working. About 2.5 minutes later, which is 2.5 minutes before the accident, he mentioned that fact to the control room.
Okay, remind me, I just put the pitot heat on. Remind me to put it off. Copy that. Ready?
The pitot heat's not hooked up on a keel probe.
Just stop it. You got enable on? Enable to stop it on.
Mysteriously, to this day, the control room gave him no response. They had an internal discussion as the clock clicked down, and internally it was commented that the pitot heat was not hooked up.
But this vital piece of information was not relayed to the pilot for more than 2 minutes. And even when it was, the information was not stated as clearly or strongly as it could have been.
And pitot heat. Well, leave it on for a moment. Yeah, we think it may not be hooked up. It may not be hooked up. That's good. I like this.
We had side discussions that should have been going on the intercom so that everybody in the control room was part of the conversation. Instead, we'd pulled our headsets aside so that we could talk to each other because we were sitting adjacent to each other. And that's another part of just control room discipline that we broke down on.
Meanwhile, the first signs of trouble were beginning to appear.
So now the pilot sees an anomaly in his airspeed. He's at 20 degrees angle of attack, and he can see that. And he says to the ground, and I briefed this many times, he said, "I'm at 277, I mean 207 knots.
And the airspeed is off, reading 277 knots at 20 AOA. Okay, pitch doublet.
Well, Anybody that's been on the program, and lots of people have been on many years, would know that 20 degrees angle of attack is somewhere around 135 knots, 140 knots, doesn't matter. It's not 207 knots.
Apparently, no one in the control room caught the possible significance of that discrepancy. And perhaps even more importantly, neither did the chase pilot, for the simple reason that he couldn't hear any of the pilot's transmissions.
We had a mechanism of hot mic, very important to the pilot in the X-31, that he'd be able to talk to the control room without having to press buttons at certain key times, especially at high angle of attack, which was not going to be a factor in this flight because it was going to go to about 20 degrees angle of attack. But it was a general operating procedure that was compounded because our hot mic system didn't work always very well. And when it didn't work, it put a lot of static in the earphones of the chase pilot who wanted to hear the hot mic to know what's going on.
So it was the one-sided nature of the communication that kept me from having the situational awareness to be able to step in and say, hey, I'm reading X knots and you guys are reading Y knots, and these two numbers should be the same, and they're not.
The X-31 did indeed have an air data problem. The unheated keel probe had frozen over in the cool, moist conditions, causing it to start giving incorrect airspeed information to the X-31's flight control computers.
In terms of the accepted risk, the failure of the pitot-static system or damage to it was well known. It was well understood. The pilot himself had simulated the failure in simulations before we even got the airplane. And it probably helped him understand that he had to get out of the airplane because the time is short when the airplane is diverging.
And we went through quite a thorough review of the hazards that we knew or could come up with based upon the design of the flight control system. And we thought we had a good handle on that. We thought we could lose the whole nose boom. We could take a bird strike, wipe out the whole nose boom, and fly home safe. As a result of that, we thought we had a pretty robust system.
The reason the team thought they had a robust system was the X-31's flight control system was designed with 3 backup reversionary modes the pilot could select in the event of an air data problem or other systems failures.
So in the case of if you saw something that was not right, or the control room saw something that was not right with respect to the airspeed system, they could tell the pilot to go to R3.
R3 was a reversionary mode that would have removed within 2 seconds the airspeed data inputs into the flight control system. The control surface response to pilot inputs would then be independent of airspeed, allowing the airplane to remain controllable for the remainder of the flight back to the landing.
The accepted risk was probably reasonable, but here's the kicker. The consequences of a failure are so high here that you really needed to put some special attention on this. The designer did by putting R3 in.
But nobody on the test team, including the pilot, realized that the X-31 was experiencing an air data problem that would require implementing the R3 reversionary system.
For several minutes, we had indications that the airspeed was becoming poor, both in the cockpit and the control room. In our last-ditch catch, nobody stood up and yelled, "Wait a minute, this can't be right."
Because had we realized what was going on, the control system had the ability to go to fixed flight control gains, and with fixed flight control gains, it would not have been a problem. They would have been able to land the airplane safely. But we just never got enough information to make the decision to do that.
We had an alternate airspeed indicator that used a different pitot tube, which would be less susceptible to icing than this special tube. It was at the pilot's right-hand knee, and he never looked at it. We had a lack of attention to the reversionary modes. Gradually, we were not thinking. We learned to depend on the control room. They're going to tell us when we need to go to R2 or R1 or R3. We need to know as pilots, which we kind of forgot, where are the safety nets? The safety nets, push the right button, didn't get the test data, but you bring the aircraft back. So if he didn't understand what was happening, we should have been constantly reminded, push the button and talk about it.
Pilot obviously wasn't concerned. His experience, probably, if you look at the control room, the pilot and everybody involved in that day's activity, he was the most experienced X-31 in that day's activity. He had been on a program since Palmdale. So he noticed something, but he wasn't concerned, and he didn't ask for help that I was aware of. And so I think the control room said, well, he's not that panicked, I'm not that panicked, and I think that fed off each other a little bit.
The team moved on to the final test point of the day, a simple automatic control response test that required only a command from the pilot to initiate. But once again, the airplane did not respond as expected.
He hits the box, presses the button, and he says, I don't get anything. Well, he didn't get anything because the box was designed not to put any input if you went beyond a certain speed, like 200 knots. So it was seeing the false airspeed of 200 plus knots. And when he pushed the button, it didn't work.
3, 2, 1, go. Doesn't do anything.
But it didn't work because something was wrong. And the control room came back and finally just kind of ignored that and said, it's all okay, RTB now.
It's almost like expecting to hear that went fine. After this program with hundreds of flights and everything going perfectly, in your mind you're hearing things that weren't happening. Everything's fine, worked fine, let's come home.
The normal operation of the system was expected that the system would identify the problems itself, that it would not be the people on the ground identifying an air data problem and calling for fixed gains. Although it was certainly capable of putting that, the expectation would be that the system would do its own self-diagnosis and identify failures.
But the failure we had was a slow failure of the tube, slowly building the ice up. So the changes in the speed were within perfectly reasonable numbers for a real airplane. Software is just not capable of detecting that failure for that system.
There was one or two people that actually knew that there was these little tiny areas that, it couldn't handle it, but that word never got out. They never stood up and said, boss, that's not quite right. You can handle it over 95 or 99% of the area, but there's really a couple little areas the automated system can't handle it. And that didn't come out till after the accident. I never did get to talk to them about it, but I just kind of felt they didn't want to stop the program, thought it was of no real issue because of the difficulty of getting to such a small area of the envelope.
But as the X-31 began to descend on its return to base, the problems caused by the failure of its air data system became far more pronounced.
We have frozen the pitot tube now, and it's stuck. It's got what it had in it, and it's going to hold that pressure. Now when you start down with a frozen pitot tube, the airspeed, what you see, the false airspeed that he saw, will decrease as he decreases altitude. But we are seeing, the control room is seeing, they have a big display, this big. The pilot is seeing every time he turns his head, he's seeing the airspeed in the HUD. And now it's perhaps at one point, it's at 150 knots. It cannot be at 150 knots. And then it's at 100 knots. And it cannot be at 100 knots. And going on down, it finally, right just before the accident, it gets to 48 knots, which is the minimum it's going to read. But the control system in the airplane is getting this wrong information. And this is a complex closed loop system, and when you put too much gain in, it will start to get unstable and it will start moving the controls, which it did a matter of seconds. And finally, it dramatically pitches up. The pilot, of course, tries to prevent that, and I'm sure the instant that he hit the forward stop and realized he was out of control, he did the natural thing, was eject from the airplane.
We were RTB, return to base, and I started to rejoin on the X-31. As I came up on his right side, about 100 yards away and closing, I saw the airplane start to go into a small wing rock that progressively got larger and larger. And as I got within about 200 feet of him, the airplane pitched up vertical. And approximately the time that I passed to beam him, I saw the pilot eject.
Okay, NASA 1, we have an ejection. We have an ejection. NASA 1, do you read? Yeah, we copy, Dana. We copy. And Sport, NASA 8584 has ejected. The aircraft is descending over the North Base area. I have a chute. Sport, NASA 850, how do you read? 850, say it again, please. Yes, sir. NASA 584 has ejected from his aircraft. The aircraft is descending north of North Base. The pilot is in the chute at this time, descending approximately 1 mile north of North Base.
So there was the knowledge and training in the simulation that taught the pilot that when he started seeing the airplane was oscillating, was not controlled, he knew that he had to get out of the airplane very fast or else the airplane would go into a tumble. And he did do that, and that saved his life. I also know that the pilot, as he was ejecting from the airplane, had thoughts of maybe I should have tried a reversionary mode. But at that point, if he would have hesitated any longer, he would have been probably lost with the airplane. So
I did not connect until after the plane departed, and while the plane was tumbling, I made the connection. Pitot system had to be frozen, and just didn't come to the realization soon enough to do anything about it in the control room.
Less than 4 minutes after the first comment about pitot heat was recorded between the pilot and the control room, the X-31 crashed just north of Edwards Air Force Base. How could such a routine operation have ended in disaster when flights with far higher risk had been completed safely? And more importantly, what can we learn from the answers to that question?
Every person involved in an experimental flight research program should actually study the mishaps of all experimental aircraft in the past 20 to 30 years. There's a lot of things you can learn because human nature doesn't change, the processes don't change. It's always the same set of contributing factors, just the names and the details change. Of the 10 things, for example, that I describe as contributing causes of the mishap, 6 of them occurred prior to the day of flight. 4 occurred within about 2 minutes. So we had a better chance of working on the 6 than we did on the 4.
In some senses, the X-31 accident started 6 years earlier when the plane was first developed and tested at Rockwell.
We had a hazard analysis from the initial design, and in the accident that had to actually get dusted off. You should never have to dust off one of those. Everybody familiar with the program, all those levels need to have a really good, comfortable feeling of what those hazards are and what is accepted in the risk. There was a redo of that analysis as we moved to NASA in '92, and I think and it was clear after the accident, not everybody really understood what that design was to the detail you needed to understand the full risk of the program. Clearly, from 1990 to 95, you have a large team turnover. We changed locations. We expanded the objectives of the program. And as time rolls on and the new people come in, not everybody has the same understanding or appreciation of the kind of vehicle we're operating. It's a special airplane. It's not the same risk as any other airplane. And to operate it every day, you really ought to have the same appreciation for the risk. And I don't think we as a team did a good job of keeping everybody that came to the program with the same level of understanding of both the design and the risk on the airplane. We shouldn't have had a control room, a pilot, and a team that day that didn't understand that fundamental fact. And it's not elaborate, it's just straightforward. The airspeed I see in the HUD is the airspeed the computer uses. If the airspeed I see has got a problem, the airplane's got a problem. And that fact, it didn't get communicated correctly from old team members to the new team members. And if it had, I don't think there would have been anybody in that room that wouldn't have yelled stop and jumped off the bridge to make it happen.
There were errors made. The pitot heat circuit breaker was disabled, but there was no placard in the cockpit to say no pitot heat. And Notices of the configuration were sent around, but here also we probably lacked one step, and that is to know that everybody got the message. It's one thing to send it out, it's another thing to verify everyone has read and understood it. And so that procedure was changed, by the way, so that people ripped off the bottom of the page and sent it back. I've seen it.
Ironically, the X-31 program also may have been a victim of its own success.
I never saw complacency in this team. I went to tech briefs, crew briefs. It was treated very professionally, and in fact, to some extent, it was treated like an experimental airplane every flight. But certainly you have to think that after hundreds of flights, excellent results, and the fact that none of these hazards, these terrible things that you predict could happen, has ever happened, it could lead you to be less sensitive to things that are happening. Maybe just a little bit of the edge comes off.
Those single point failures were identified, and we made some actual changes to the design of the airplane to account for that. And again, that was in 1989. Why all those were there and what the concerns were and how to mitigate them and how to worry about them we hadn't had any problems with that for 5 years. And I think, again, the complacency just got built into the team. It worked fine. We never had a problem. And those little hairs on the back of your neck weren't geared to stand up when people started having airspeed problems.
Our control rooms used to have a saying on them to prepare for the unexpected and expect to be unprepared. And I think that's a truth in the flight test business, that that we need to keep that in mind continuously. I wish that sign was still up there, because that reminder needs to be enforced all the time.
Well, certainly in the case of the X-31, we were returning to base after 2 exhausting days, 7 flights. Ship 1 was now going into the boneyard, or at least it was being retired from the test program. And so we're finally finished. Is everybody paying attention like they should be? Obviously not.
And while the X-31 program flights were highly successful, they did not include an element that might have helped prime the program team to take the one mitigating action that could have brought the X-31 home safely.
We've debated amongst ourselves whether we actually would have been able to convince anybody to use the fixed gain system, because there was not an obvious need for it. The pilot may have been better prepared when things started to go awry to select fixed gains, but I don't know if we ever really would have done it in that situation, because we didn't have a real problem. We did have a real problem, but it hadn't been diagnosed as a real problem.
On a previous program, the X-29 program, we had the same sort of thing. We had an analog reversion mode, a digital reversion mode, and the normal mode of the airplane. We routinely at every test point selected those backup modes, flew them around, so the pilots were much more familiar and much more comfortable with selecting those modes. On the X-31 program, we never selected those modes intentionally. We only used them when we had a sensor failure or the system told us to select those modes.
On the day of the mishap itself, there were additional links added to the chain. There were unusual weather conditions that created an uncommon and unexpected kind of flight hazard. And the team was working with a flawed hot mic system that kept the chase pilot from hearing critical communications from the X-31 pilot.
So, some links in the chain are already built there. Management links. Control room is now talked internally. They've heard some things. They haven't said anything. Some more links are built. We got this chain is building now. The chase pilot didn't hear anything about this, didn't know that he didn't know anything was wrong with the airplane until he saw the airplane pitch up and the pilot jump out. Whereas he could have stopped this anytime.
At any rate, it's a total team concept, and the chase pilot has to be part of that team. The team has to have total communication. So the use of a hot microphone frequency that did not allow the chase pilot to stay up with what was going on with the airplane was essentially keeping me from doing my job, at least at a certain level. And that's one of the things that we changed in the way we do business here at Dryden, is to allow the chase pilots either access to the hot mic or to ensure that all critical communications are transmitted so that all the players are kept up to speed with what's going on. And that was a direct fallout of how the X-31 operation was handled that day.
If one or more of these contributing factors had been caught and addressed prior to January 19th, the chain of events leading up to the accident might have been broken before the flight even took place. Yet there were still opportunities to avoid the mishap, even in the last few minutes of the X-31's flight. So why didn't the team manage to recognize, communicate, and respond to the X-31's pattern of anomalies in time?
So we were seeing inconsistencies between the data from the aircraft system and what we knew of the physics of the problem, that it could not be, that you could not have that airspeed and that angle of attack simultaneously. And for me, I just remember thinking, gosh, I can't wait till we get the data from this flight because I want to see what's going on. I knew there was an anomaly. We had talked about it between the engineers. We didn't talk about it on the intercom, though. It was sidebar conversations in the control room.
Well, many of us are engineers, and we see an issue. Oh, this is interesting. I wonder what's causing that. And you start thinking about it and trying to figure out what is the answer. In the meantime, the seconds are clicking by. And really, the right response is, something's going on I don't understand. Let's call a halt here and let's just figure it out.
We should have, at the first call of an airspeed failure, puckered up. Whether you're RTB at that point or not, it wouldn't have changed. The kind of failure that was occurring should have triggered a lot of emotion anywhere in the flight envelope.
In the case of any discrepancy, anything that doesn't sound right, feel right, smell right, let's stop and think it over. And I think that kind of attitude has been built in now into the control room, mission control room processes since then.
We were flying lots of flights. At the peak of the program, there would be days when there would be 5 flight days. I think on that particular day, we were only doing 3 flights. And it was the last flight of the day. It was the last flight for the first airplane. And we had completed all the test points for that mission. In addition, we were going through the RTB, or return to base checklist. And at that point, every one of us kind of relaxed. Like I said, what was going through my mind is, I can't wait to get this data. Something funny is going on, and I want to figure it out. And that's another lesson learned, that when we talk about it all the time, the mission's not over till the airplane's on the ground and the engine's shut down. And you see it a lot in the control rooms. We start getting ready to land, and everybody relaxes a little bit. And that's a lesson I've carried with me, is you need to continue the vigilance there in the flight.
Communication is what it's all about. So everybody, we have to have the communication links. We didn't have it to the chase. Hot mic was a contributing factor. We didn't have it in the control room. We discussed things internally, was not transmitted to the pilot. We have to have an environment and built where people can speak up when they think something's wrong. They don't have to be right. If they're concerned, they should be able to speak their mind, put their hand up, and we stop the train. And then we say, no, you weren't right, it's okay. Fine, we go on. We didn't do that. We never stopped the train.
We had a problem, and we didn't stop, not only testing, we didn't stop flying and come home. But you can't stop for every problem. I mean, that's unrealistic. You have problems in flight. The combination that went with that is we didn't understand the severity of the problem. So you have to understand your vehicle and the consequences of failures. And if one of those failures has a serious consequence, you need to stop and come home.
Clearly, there are lessons to be learned in the entire progression of events that led up to the X-31 mishap. And yet, the X-31 program did not end with that crash. The next chapter of its story is an equally important reminder of why flight test remains such a valuable step in proving a concept or technology, despite the hazards that come with the territory. The X-31 had been scheduled to fly at the Paris Air Show in June of 1995. But after the loss of one of the 2 X-31 ships less than 6 months before the show, it seemed an impossible goal.
Having lost the airplane, pretty much everyone thought that's it. Because flying the kind of maneuvers that this airplane can do at 500 feet sounded a lot riskier to me after you lose an airplane. The team really talked a lot about this and decided that it did not want to end this program on a low note. And so We made the decision to press on with the Paris Air Show.
A huge thing to sign up for was to take an airplane that just crashed and to turn it around to go do a low altitude, high angle attack flight demonstration. That took a lot of guts on everybody's part and a lot of good engineering work to make that happen.
We actually flew the X-31 84 days after the mishap. And this required the board to reach its conclusions, to write a report, for the team to react to all of the issues and problems and contributing factors brought up, solve the problem, and get it into an airplane and get it qualified for first flight. It was all done in 84 days. It does tell you about the quality of the team.
Cool. Wind a little right. And very covenant.
Totally different aeroplane which will demonstrate a most remarkable flying ability. It is the X-31 technology demonstrator.
You know, after the mishap, I think the program made a spectacular recovery and made one of the finest appearances ever at the Paris Air Show. The airplane did things that no other airplane could do. The Russians had demonstrated post-stall maneuvers with the Cobra, but it was really an open loop maneuver. They pulled back on the stick and then you flew out of it at the end. Whereas the X-31 just demonstrated the ability to control all axes of the airplane, pitch, roll, and yaw simultaneously while operating at the extremes of the flight envelope.
So, a fantastic air show, absolutely the most spectacular I've ever seen, and I saw every one of them. And I stood with the crowd on some of them, and I was in the control tower on others, and out right underneath it at other times. But to be with the crowd and watch, even hardened veterans, military, had no concept of what it could really do, and seeing it was jaw-dropping for the crowd. It was spectacular.
The announcement that the X-31 was next to fly, as you look down the row of chalets, you see all the people coming out of the chalets, out against the railing to watch the flight.
If the events leading up to the X-31's mishap are a reminder of how much vigilance is required in order to mitigate the risks inherent in a flight test program, the X-31's Paris Air Show performance was a reminder of why those risks are still worth undertaking.
Flight test of all kinds is inherently dangerous. There are risks involved in it. Never can you or anybody else bring it to zero. Well, you can. That's keep the airplane in the hangar. Don't fly. Well, if you don't fly, you don't move forward, you don't discover, you don't prove things. So you need to take some risks, but you need to do it in a controlled fashion.
The reason we spend time on looking at these accidents is that there aren't many accidents. We don't lose many airplanes in flight research activities at Dryden. We haven't over the years. And so when you do have one, you better learn everything about it. In fact, you should do the same thing for close calls.
The lessons to be learned. Don't assume that they've been learned. We can always, at every new group, will have to learn the same lessons, and you don't want to do it the hard way with an accident. Safety is everybody's business. Flight test safety is everybody's business on the team, and there are no processes. You have to have processes, but there are no perfect processes that will not require good judgment from all levels of the program.
If you're a program that's been operating for a long time, potentially, you've got a lot of turnover, you're in your mature years, all your documentation is years old, maybe you better make sure that all your new people are as good as your old people, that you've reviewed your documentation and it's still correct and you all understand it, and that what you're doing today still makes sense from how you started. So maybe one of those, if you're in that area, you ought to take a look at yourself.
It always is clear what you should do after the fact, or should have done rather, and nobody thinks it's ever going to happen to them. To lose judgment, to lose this communication link, to not do the right things.
So what is the message? What is the message for the team? It may mean that I am a part of the chain. And that if I don't catch this, and if other people don't catch their mistakes, we will run through the entire chain and lead to a mishap. So it means that every individual in the program from beginning to end, no matter what the job is, from the highest level job to the lowest level job in terms of detail, they have to take it very seriously. And that's a message that you have to keep promoting, pronouncing, and explaining. It sounds trite, but everybody is responsible for safety. If you think some safety office analysis is going to find the things, they won't. Mishaps can occur everywhere, but the point is you have to fly safely, but fly.
March is Women's History Month, and there are women at NASA contributing every day to the success of our current missions and paving the way for future generations to reach for the stars. Mallory Jennings is the first female system manager for the Extravehicular Mobility Unit, or EMU. The EMU is the spacesuit worn by astronauts during a spacewalk outside the International Space Station. Mallory coordinates all the engineering aspects, from hardware to new technologies. From communications to thermal protection to oxygen, all the systems work together to protect astronauts from the harsh environment of space. NASA is designing new spacesuits to use for Artemis missions to the moon. Leanna Rodrigues is leading the team using new technologies to develop and build the Exploration EMU spacesuit. She's the inspirational leader who will help our next moonwalkers. They will have more natural mobility and a robust life support system to explore the lunar surface and beyond. Have you ever driven a remote control car? Now, imagine it was on another planet. Farah Alibay is a systems engineer working on our new Mars rover, Perseverance. As the rover moves across the red planet, the systems she worked on make sure the rover knows the direction it's pointed and updates that position for teams back on Earth. She spent last summer testing our new rover's capabilities in a giant sandbox with a replica of the rover. Not only do we study other worlds, we also study Earth, our very own planet. From space, the Landsat program maps Earth's surface to provide information about our resources and environment. Melody Jam is leading the development of an instrument on the newest Landsat spacecraft that will launch this September. That instrument will measure the surface temperatures of our planet. Lola Fatinyimbo Age uses satellite data and imagery to study forests. Her research reveals how our ecology has changed over time and works to predict how it might change in the future. Lola is working to make our planet a better place. Erica Alston inspires students through the Space Grant Program. As an engineer, she used our satellite data to focus on air quality and climate change. Now, she expands opportunities for young Americans to understand and participate in our space projects, just like she did. Erica is a role model for future generations. Did you know the skills used to build spacecraft were also used to develop ventilators for COVID-19 patients? Michelle Easter is an expert in mechatronics, which is the design, assembly, and test of mechanisms controlled by electronics. She was part of the team that designed low-cost ventilators in response to the pandemic. Michelle was the first female to join the mechatronics group at our Jet Propulsion Laboratory. Lori Grindle is responsible for flight programs and projects at our Armstrong Flight Research Center. Lori oversees cutting-edge aerospace concepts and technologies, including experimental aircraft and unmanned aircraft systems. flight research and testing is vital in the development of new aircraft. Women's contributions at NASA reach other solar systems. Nicole Colon's work involves the discovery and characterization of exoplanets. These are planets that orbit around other stars. Using several NASA observatories, she was able to study a puffy exoplanet with low density, similar to styrofoam. Nicole's work is expanding what we know about the universe. At NASA, women innovate, break barriers, and explore the unknown. The list of their accomplishments is being built upon every single day. This March, take a moment to recognize the contributions of women in the world around us, and together we celebrate Women's History Month. March is Women's History Month, and there are women at NASA contributing every day to the success of our current missions and paving the way for future generations to reach for the stars. Mallory Jennings is the first female system manager for the Extravehicular Mobility Unit, or EMU. The EMU is the spacesuit worn by astronauts during a spacewalk outside the International Space Station. Mallory coordinates all the engineering aspects from hardware to new technologies. From communications to thermal protection to oxygen, all the systems work together to protect astronauts from the harsh environment of space. NASA is designing new spacesuits to use for Artemis missions to the moon. Leanna Rodrigues is leading the team using new technologies to develop and build the Exploration EMU spacesuit. She's the inspirational leader who will help our next moonwalkers. They will have more natural mobility and a robust life support system to explore the lunar surface and beyond. Have you ever driven a remote control car? Now, imagine it was on another planet. Farah Alibay is a systems engineer working on our new Mars rover, Perseverance. As the rover moves across the red planet, the systems she worked on make sure the rover knows the direction it's pointed and updates that position for teams back on Earth. She spent last summer testing our new rover's capabilities in a giant sandbox with a replica of the rover. Not only do we study other worlds, we also study Earth, our very own planet. From space, the Landsat program maps Earth's surface to provide information about our resources and environment. Melody Jam is leading the development of an instrument on the newest Landsat spacecraft that will launch this September. That instrument will measure the surface temperatures of our planet. Lola Fatimimbo Age uses satellite data and imagery to study forests. Her research reveals how our ecology has changed over time and works to predict how it might change in the future. Lola is working to make our planet a better place. Erica Alston inspires students through the Space Grant Program. As an engineer, she used our satellite data to focus on air quality and climate change. Now, she expands opportunities for young Americans to understand and participate in our space projects, just like she did. Erica is a role model for future generations. Did you know the skills used to build spacecraft were also used to develop ventilators for COVID-19 patients? Michelle Easter is an expert in mechatronics, which is the design, assembly, and test of mechanisms controlled by electronics. She was part of the team that designed low-cost ventilators in response to the pandemic. Michelle was the first female to join the mechatronics group at our Jet Propulsion Laboratory. Lori Grindle is responsible for flight programs and projects at our Armstrong Flight Research Center. Lori oversees cutting-edge aerospace concepts and technologies, including experimental aircraft and unmanned aircraft systems. Flight research and testing is vital in the development of new aircraft. Women's contributions at NASA reach other solar systems. Nicole Colon's work involves the discovery and characterization of exoplanets. These are planets that orbit around other stars. Using several NASA observatories, she was able to study a puffy exoplanet with low density similar to styrofoam. Nicole's work is expanding what we know about the universe. At NASA, women innovate, break barriers, and explore the unknown. The list of their accomplishments is being built upon every single day. This March, take a moment to recognize the contributions of women in the world around us, and together we celebrate Women's History Month.
Locked and we are good to send that command. You have 31 minutes and 32 seconds for our support. Go for status buffer dump.
What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
The Webb telescope will be groundbreaking because it has capabilities that are different than the Hubble Space Telescope.
We have equipment that is so much more powerful than anything we've ever had before that it's almost impossible to tell what we will discover.
Hubble's accomplishments include something called the deep fields, looking out into space and collecting light, sometimes for many days. These deep fields have revealed visually to us a universe absolutely teeming with galaxies, hundreds of billions of galaxies.
One of the neat things about the ultra deep field, and one of the things that made it so unique was how long it took us to take that image. There's an exposure time that's expressed, I think it's 11.2 days. There's a very, very long exposure time. But probably what's more important is how many orbits it took us to do that. 400 orbits of Hubble data to take that image. You only get 15 orbits a day. To take 400 orbits and say, we're going to observe this one spot in the sky for 400 orbits. And the really unique thing about that was they picked a spot where there wasn't anything. They looked and they said, there's absolutely nothing here. And they said, you want to spend 400 Hubble orbits looking at nothing? And they said, yes, because we want to see what it can see. And I think the results from the science, I mean, it was amazing. What they saw was spectacular.
Hubble had spent 2 weeks taking pictures of empty places in the sky, and they saw they weren't empty at all. They were thousands and thousands of galaxies.
We were amazed how many galaxies we've found, and we continue to go back to that portion of the sky to increase that visibility.
The Hubble Space Telescope is an outstanding time machine. It's incredibly important for our studies with the Hubble Space Telescope to realize that when we're looking at a galaxy, we're seeing it as it was millions of years ago, sometimes billions of years ago. It's taken that long for the light to get to us.
What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
What Hubble has revealed is that the universe has in fact changed over these billions of years of time. The early galaxies, the very distant ones as we see them, are simple. Sometimes they're messy looking, they're small, they haven't had time yet to form that grand spiral structure. Over time, we see galaxies actually merging with other galaxies and growing bigger and bigger, and those mergers can look like train wrecks in our Hubble images.
These very, very deep exposures that Hubble has been able to take, we have seen right to the edge of the universe, 13.5 billion years. When Hubble was first designed and envisioned, it was never thought it could actually see that far out. But because of the advances in the instruments that we've been able to put up on the telescope, and also the cleverness of the scientists, they've come up with very interesting observing scenarios, doing these really deep exposures where we just sit there for orbit after orbit after orbit, gathering the photons. We've been able to push Hubble out very, very far.
As Hubble looks out into these fields of galaxies, we sometimes see clusters of galaxies. These are galaxies that are held nearby each other by their mutual gravity. These clusters are massive conglomerations. There's so much mass that they have an actual observable impact on space-time itself. Einstein predicted that mass distorts space, but we didn't realize we could actually see the effects of that. But with Hubble, we have been able to see distortions in space around clusters of galaxies. The way we see that is when light from a background galaxy travels through that cluster of galaxies or around it due to this gravitational lensing effect. The lensing also magnifies that background galaxy, so if we look in some of these distorted arcs, we can see more detail than we would ever have been able to see without gravitational lensing, nature's boost.
There are observations where we're explicitly looking for the lensing and they're getting science out of that that just otherwise would just not be doable. Hubble has really taken that to a next level. It's doing large amounts of astrophysics that it's just never been able to do before.
Some of what we're doing with Hubble is to prepare for the new James Webb Telescope, which we anticipate launching in 2021, which will be able to see farther into the infrared part of the electromagnetic spectrum. That enables us to see some galaxies that are difficult for Hubble to see because they're so far away that their light is traveling through us through expanding space and gets stretched out into redder wavelengths, often far into the infrared part of the spectrum, even sometimes beyond what Hubble is able to detect well. The Webb telescope will give us more information about some of those very distant galaxies.
The James Webb Space Telescope is the follow-on telescope after the Great Hubble Telescope. It extends the discoveries of Hubble into the infrared spectrum region. We think that the first objects that grew out of the Big Bang material probably happened in about 100 million years after the start. And we think the Webb telescope can pick them up. They're rare, they're hard to find, but they should be there. The farthest we've been able to see with the Hubble telescope goes back about 800 million years after the expansion began. So we think we get much closer to the first objects with the Webb telescope.
Hubble gives information that the Webb telescope cannot give about visible and ultraviolet emission from things in the universe. And when we have all that information coming in at the same time, it's like a banquet of scientific return.
Now when we get the complete picture of every wavelength you can possibly see from ultraviolet to infrared, we hope to have the story of the growth of the first galaxies from the primordial material. So that will be a huge accomplishment that depends on both pieces of equipment, the Hubble telescope and the James Webb telescope working together.
So astronomers are very excited about this probability that we'll have both the Hubble Space Telescope and the Webb telescope operating at the same time for quite a few years. That will give us an abundance of new understanding about the universe. And already right now with Hubble, we're doing preparatory observations for the Webb telescope. We're using Hubble to do things, for example, like surveying distant galaxies to find out which ones would be prime targets for the Webb telescope. In fact, scientists around the world are proposing observations with Hubble right now specifically to help us learn information that will be useful for making the best use of the Webb telescope as soon as it's launched and gets going in its science observations.
I think the Hubble telescope has been the most productive science instrument ever built. In astronomy, there's what we knew before Hubble, and now there's what we know after Hubble. They're so different. Of course, Hubble has now had a life of 30 years, so it's had a long time to make this revolution happen. So it's not all at once. It's a gradual revolution, but it's still a huge revolution. Technology has changed dramatically over the 30 years of life of the Hubble telescope. So you couldn't even have imagined when the Hubble was launched that we would have the wonderful cameras and spectrometers that we fly today. We figured out how to send astronauts, we trained the astronauts, we figured out what instruments could be put in, we figured out how to repair everything that went wrong on the Hubble, and it's still alive. It's today, 30 years after launch. And I am so thrilled to say that our people were able to do that. That's the operations team that makes this possible. It's a miracle as far as I'm concerned, because it didn't have to be that way, but they made it happen.
There is one place where we're seeing climate change unfold faster than anywhere else on Earth. Here. In fact, temperatures in the Arctic and boreal regions are rising nearly 4 times as fast as those in the mid-latitudes. That's why NASA has teamed up with local partners to better understand the vulnerability and resilience of these ecosystems, while also gathering valuable data that will help future Earth-observing satellites. From space, air, and on the ground, we'll see how scientists are piecing together the story of the Arctic, from how it is changing to what that means for our planet. Because as they say, what happens in the Arctic doesn't stay in the Arctic.
PPA is engaged. And we're radiating.
One of the best ways to track how an environment is changing is to observe it from above. But where weather and vegetation can make it difficult to see the ground with the naked eye, specialized radar can pierce the clouds to give us a crystal clear look at the landscape. This special device, weighing nearly 1,000 pounds, collects data about soil moisture, vegetation, permafrost, and other environmental processes on the ground below. In fact, it's so precise that NASA developed a special system for pilots to fly the exact same flight path year after year to get an accurate reading as to how a landscape is changing over time.
So with the airborne data, we can target exactly where we want to go and exactly when we want to go there, and we get very high resolution data, so we can have a really clear picture of what's on the ground.
That's Dr. Liz Hoy, senior scientist for NASA's ABOVE mission. ABOVE has spent the last 7 years studying environmental changes in the Arctic and boreal regions. The mission uses satellite, airborne, and ground data to get a complete picture of what is unfolding in these ecosystems.
So our satellite data gives us a very broad picture of what's happening all over the landscape. And then with our airborne data, we can target specific locations and times when we want to get imagery. And then we can compare both our satellite and our airborne data with what's happening on the ground when we have teams actually out on the ground making measurements. And putting all that together is really where we get a lot of the power of what we're able to study.
And it all gets put together in Alaska. On the ground, these large dishes are used to communicate with NASA's Earth-observing satellites. Here, the data is downloaded and made public, which helps scientists connect the dots between what we see from space and on the ground. But why are these dishes in Alaska?
So the reason why a station like ASF is built in Alaska is because Earth-observing satellites, if you think of their orbits, they converge in the polar regions. So in Alaska, we can see the same satellite more often than in the lower 48.
In fact, this facility is in the perfect position to receive data from one of NASA's latest Earth-observing missions. NISAR is an upcoming satellite that will be launched by NASA in collaboration with the Indian Space Research Organization. It will use radar similar to what is flown on NASA airborne missions, like 4above, to measure fine, centimeter-scale changes in Earth's surface.
What's interesting and unique about NISAR is that it's going to cover the globe regularly every 12 days. And it's going to do it at a wavelength or frequency range, so-called L-band frequencies, that are very useful for doing Earth observation. L-band will allow us to study ecosystems changes and deformations of the Earth's surface with higher accuracy and better spatial coverage than we can with current systems in space.
And in the Arctic, some of the most pronounced environmental changes satellites can observe are happening right down the road. And it all starts with this stuff. Permafrost is frozen earth, be it ice, soil, or even organic material that has been frozen for 2 or more years. Most of Alaska and northern Canada has permafrost beneath a thin, active layer of soil. Problem is, when permafrost does thaw, it can wreak havoc on infrastructure and upend ecosystems.
Not all permafrost contains ice, but here in interior Alaska, we have frozen soils with massive amounts of ice. There are very large ice wedges as big as garages. And so when that ice melts, the ground surface collapses and the sinkholes can fill with water. When that happens, new little ponds form, thermokarst ponds.
And as thermokarst ponds form, microbes in the soil feast on the newly thawed organic material, releasing methane into the atmosphere, an extremely potent and flammable greenhouse gas. These newly formed thermokarst ponds give us an insight as to what is going to happen in the future.
What we're seeing at this lake is that the emissions are 10 times higher than the rest of the lakes and wetlands in the Arctic. And it's being fueled by thawing permafrost.
Scientists are working with Above and NASA's UAVSAR radar to study how these lakes are evolving as the climate continues to warm. But it's not just thawing permafrost that is reshaping the Arctic. It is also wildfire. In higher latitudes, forests are adapted to burn about once every century. But with warmer temperatures comes more fires. And why is this? Partially because of this stuff called duff, forest debris that slowly builds up on the forest floor, about 1 inch every 17 years. And because of the cold winters, it doesn't decompose.
It doesn't have roots, so it's completely dependent on relative humidity for moisture. So it actually dries very rapidly in warm, dry conditions like we often have here in the summer.
Which means with warmer temperatures, duff becomes a potent fuel for fires.
Most Alaskans are vulnerable to wildland fire, and with climate change, it seems that the imprint on the landscape is growing, and so more and more communities are vulnerable.
When a wildfire comes through, what we're really seeing is it's not just the trees that are burning, but it's the soil layer that's burning as well. And so when that fire comes through and it burns that soil layer, it's like you're taking off the lid of a cooler where everything is frozen below. And so as that soil comes off, then we start to see the ground start to thaw, and permafrost is thawing there. And so as we see those changes happening, we're actually creating more climate change over time. So wildfires are releasing carbon gases into the atmosphere, and then as permafrost thaws, it too is releasing carbon gases into the air, which then can create warmer conditions, which can allow for more wildfire and more thaw. So you really see this cycle that continues up in boreal forests and Arctic areas over time.
So the bad news is that as human-caused climate change continues to impact the Arctic and boreal landscapes, those living both near and far will continue to feel its effects. But the good news is that there is a team of dedicated scientists across a variety of disciplines that are working together to give us a complete picture of these ecosystems and how they are changing. Because this collective knowledge is key to understanding how we can lessen our impact.
March is Women's History Month, and there are women at NASA contributing every day to the success of our current missions and paving the way for future generations to reach for the stars. Mallory Jennings is the first female system manager for the Extravehicular Mobility Unit, or EMU. The EMU is the spacesuit worn by astronauts during a spacewalk outside the International Space Station. Mallory coordinates all the engineering aspects from hardware to new technologies. From communications to thermal protection to oxygen, all the systems work together to protect astronauts from the harsh environment of space. NASA is designing new spacesuits to use for Artemis missions to the moon. Leanna Rodrigues is leading the team using new technologies to develop and build the Exploration EMU spacesuit. She's the inspirational leader who will help our next moonwalkers. They will have more natural mobility and a robust life support system to explore the lunar surface and beyond. Have you ever driven a remote control car? Now, imagine it was on another planet. Farah Alibay is a systems engineer working on our new Mars rover, Perseverance. As the rover moves across the red planet, the systems she worked on make sure the rover knows the direction it's pointed and updates that position for teams back on Earth. She spent last summer testing our new rover's capabilities in a giant sandbox with a replica of the rover. Not only do we study other worlds, we also study Earth, our very own planet. From space, the Landsat program maps Earth's surface to provide information about our resources and environment. Melody Jam is leading the development of an instrument on the newest Landsat spacecraft that will launch this September. That instrument will measure the surface temperatures of our planet. Lola Fatinyimbo Age uses satellite data and imagery to study forests. Her research reveals how our ecology has changed over time and works to predict how it might change in the future. Lola is working to make our planet a better place. Erica Alston inspires students through the Space Grant Program. As an engineer, she used our satellite data to focus on air quality and climate change. Now, she expands opportunities for young Americans to understand and participate in our space projects, just like she did. Erica is a role model for future generations. Did you know the skills used to build spacecraft were also used to develop ventilators for COVID-19 patients? Michelle Easter is an expert in mechatronics, which is the design, assembly, and test of mechanisms controlled by electronics. She was part of the team that designed low-cost ventilators in response to the pandemic. Michelle was the first female to join the mechatronics group at our Jet Propulsion Laboratory. Lori Grindle is responsible for flight programs and projects at our Armstrong Flight Research Center. Lori oversees cutting-edge aerospace concepts and technologies, including experimental aircraft and unmanned aircraft systems. Flight research and testing is vital in the development of new aircraft. Women's contributions at NASA reach other solar systems. Nicole Cologne's work involves the discovery and characterization of exoplanets. These are planets that orbit around other stars. Using several NASA observatories, she was able to study a puffy exoplanet with low density, similar to styrofoam. Nicole's work is expanding what we know about the universe. At NASA, women innovate, break barriers, and explore the unknown. The list of their accomplishments is being built upon every single day. This March, take a moment to recognize the contributions of women in the world around us, and together we celebrate Women's History Month. March is Women's History Month, and there are women at NASA contributing every day to the success of our current missions and paving the way for future generations to reach for the stars. Mallory Jennings is the first female system manager for the Extravehicular Mobility Unit, or EMU. The EMU is the spacesuit worn by astronauts during a spacewalk outside the International Space Station. Mallory coordinates all the engineering aspects, from hardware to new technologies. From communications to thermal protection to oxygen, all the systems work together to protect astronauts from the harsh environment of space. NASA is designing new spacesuits to use for Artemis missions to the moon. Leanna Rodrigues is leading the team using new technologies to develop and build the Exploration EMU spacesuit. She's the inspirational leader who will help our next moonwalkers. They will have more natural mobility and a robust life support system to explore the lunar surface and beyond. Have you ever driven a remote control car? Now, imagine it was on another planet. Farah Alibay is a systems engineer working on our new Mars rover, Perseverance. As the rover moves across the red planet, the systems she worked on make sure the rover knows the direction it's pointed and updates that position for teams back on Earth. She spent last summer testing our new rover's capabilities in a giant sandbox with a replica of the rover. Not only do we study other worlds, we also study Earth, our very own planet. From space, the Landsat program maps Earth's surface to provide information about our resources and environment. Melody Jam is leading the development of an instrument on the newest Landsat spacecraft that will launch this September. That instrument will measure the surface temperatures of our planet. Lola Fatinyimbo Age uses satellite data and imagery to study forests. Her research reveals how our ecology has changed over time and works to predict how it might change in the future. Lola is working to make our planet a better place. Erica Alston inspires students through the Space Grant Program. As an engineer, she used our satellite data to focus on air quality and climate change. Now, she expands opportunities for young Americans to understand and participate in our space projects, just like she did. Erica is a role model for future generations. Did you know the skills used to build spacecraft were also used to develop ventilators for COVID-19 patients? Michelle Easter is an expert in mechatronics, which is the design, assembly, and test of mechanisms controlled by electronics. She was part of the team that designed low-cost ventilators in response to the pandemic. Michelle was the first female to join the mechatronics group at our Jet Propulsion Laboratory. Lori Grindle is responsible for flight programs and projects at our Armstrong Flight Research Center. Lori oversees cutting-edge aerospace concepts and technologies, including experimental aircraft and unmanned aircraft systems. Flight research and testing is vital in the development of new aircraft. Women's contributions at NASA reach other solar systems. Nicole Cologne's work involves the discovery and characterization of exoplanets. These are planets that orbit around other stars. Using several NASA observatories, she was able to study a puffy exoplanet with low density, similar to styrofoam. Nicole's work is expanding what we know about the universe. At NASA, women innovate, break barriers, and explore the unknown. The list of their accomplishments is being built upon every single day. This March, take a moment to recognize the contributions of women in the world around us, and together we celebrate Women's History Month.
Artemis systems are ready to fly astronauts, a hot fire test of an Artemis rocket engine, and educating and inspiring the Artemis generation. A few of the stories to tell you about this week at NASA. After extensively reviewing data since last year's successful uncrewed Artemis 1 flight test around the moon and back, NASA has confirmed initial observations that the agency's Space Launch System rocket, Orion spacecraft, and ground systems are ready to fly astronauts on missions to the moon. The agency plans to do just that on Artemis 2 by sending an astronaut crew around the moon and back. On March 8th, engineers at our Stennis Space Center conducted this year's third hot fire test in the current test series to certify the redesigned RS-25 rocket engines. 4 of the engines will help power our Space Launch System rocket on future Artemis missions to the moon. Second Gentleman Douglas Emhoff, NASA astronaut Yvonne Kagel, and NASA Ames Center Director Eugene Tu joined students and their families at an Oakland, California educational event hosted in honor of Women's History Month. The event featured hands-on STEM activities and NASA items to inspire the students to learn about our Artemis program, which will land the first woman and person of color on the moon. NASA's Imaging X-ray Polarimetry Explorer, or IXPE, captured the light blue color in this new image of a pulsar wind nebula in the constellation Vela. The light blue represents the first ever X-ray polarization data for Vela. The pulsar itself is near the center of the image. Measuring polarization could improve our understanding of how cosmic objects like pulsars accelerate particles to high speeds.
It's extremely exciting. In my lectures, there are always young people in the audience, and they always want to know when they're bringing it back, and I always say, I don't think ever. I think NASA, they realizes that they have two marks, so to speak, but somehow they can be made to coexist. We had to analyze what had been done by NASA in the past. Finally, we realized that we had to have a unifier, something that was very strong to hold it all together. So over the process of working on it over the first month, I think we got simpler and simpler with our solutions so that it would work miles away on a T-38 or a rocket or a space shuttle. We were trying to embody in the logo innovation. The organization still had aeronautics as well as space, and so that you see a kind of nose cone design inside of the A's and propulsion, kind of upward thrust. Great simplicity, but still movement.
Roger, roll, Discovery.
The term worm came out of Florida in a newspaper down there, and it was meant to be derogatory, and I personally thought it was very derogatory. And eventually, over the years, the worm became a term of endearment, but it wasn't meant that at all in the beginning. When they started producing apparel a couple of years ago, they found out how young people in particular really like this program, and so they've allowed it to kind of come back to life on its own. It's validation, I think, of the sort of timeless approach that we brought to this. Space is about the future, and if we can still hang in there, and if it still represents that, then it's quite a victory, I think. Aesthetics aside, the goal was to do that, to hold up for decades, and apparently it's got better legs today than it did then.
Have you ever heard that something called the ozone layer is thinning? Or that your aerosol hairspray is what's causing it? Or that it leads to more severe sunburns and UV rays? This is referring to the ozone hole. But what exactly does it all mean? Welcome to Ozone 101. The ozone hole's proper name is actually the Antarctic ozone hole because when it forms over Antarctica. But before we get into what that is, let's first talk about what ozone itself is. Ozone is a gas comprised of 3 oxygen atoms. About 90% of the Earth's ozone exists in the stratosphere, the layer of the atmosphere that extends from 8 to about 30 miles above the Earth's surface. In fact, the stratosphere is often referred to as the ozone layer. Ozone acts as a sunscreen around the Earth, filtering out harmful ultraviolet radiation, or UV rays, which are mainly absorbed in the stratosphere. Without an ozone layer, UV radiation would sterilize the Earth. With a damaged but still present ozone layer, there would be more sunburns, more skin cancer cases, increased cases of eye damage, the wilting and loss of trees and plants, and significantly lessened crop yields. Suffice it to say, ozone is pretty important for the planet. So, what causes the ozone hole? There are several major factors that together lead to the destruction of ozone, thus creating the ozone hole. Those factors are 1. Very strong winds around the South Pole, or the polar vortex. 2. The sun's rays. 3. Chlorine and bromine compounds from ozone-depleting substances. And 4. Cold temperatures below negative 109 degrees Fahrenheit in the stratosphere, which form a specific kind of cloud, polar stratospheric clouds. The polar vortex forms in the southern hemisphere stratosphere during the winter as temperatures drop. And when sunlight returns to Antarctica in late winter and early spring, temperatures are still cold enough to form polar stratospheric clouds, and now there's also sunlight. Chemical reactions take place on the cloud particle surfaces, converting unreactive forms of chlorine and bromine into reactive chemicals. The vortex acts as a sort of container, confining the contents of the Antarctic stratosphere within its bounds, allowing the reactive chlorine and bromine compounds to destroy ozone molecules. That's when depletion can occur on a large scale. With the presence of sunlight, the reactive chlorine and bromine compounds produced during winter begin to deplete ozone molecules by stealing one of their oxygen atoms, leaving just oxygen gas, or O2, in its wake. As long as the polar stratospheric clouds are present, these reactions will occur over and over again, until the ozone is nearly gone. This forms what we call the ozone hole, but that's really a misnomer. It's actually more of a thinned layer. In mid to late spring, the vortex begins to break up, and the polar air depleted of ozone is mixed back into the rest of the southern hemisphere. The ozone hole is gone. Ozone depletion has still occurred, it's just no longer all concentrated in one small area. It's spread around the atmosphere. So why is the ozone hole bigger and longer lasting in certain years? Well, it all comes down to weather. Just like some winters are colder and longer than others on the Earth's surface, the same goes for weather in the stratosphere. If the Antarctic stratosphere stays cold, the polar vortex and the ozone hole within it will persist. And in years with cold springtime temperatures, the polar vortex and the ozone hole are large. Make no mistake, ozone depletion is not a natural thing. It stems from human emissions of chemicals called chlorofluorocarbons, or CFCs. In the early 1900s, refrigerators used toxic gases like ammonia and methyl chloride as refrigerants. Unfortunately, this led to fatalities as the toxic gases leaked out of the appliances. So the search began for a non-toxic and non-flammable chemical that could be used as a refrigerant. Thus, the CFC was born. There are many types of CFCs, but the two most common are CFC-11 and CFC-12. In the 1930s, the production and consumption of CFCs began to skyrocket. By the early 1980s, over 300 million pounds of CFC-11 alone were being released into the atmosphere each year. Then, in 1985, British researcher Joe Farman and his colleagues published their research on large seasonal ozone losses over Antarctica. Thanks to the combined efforts of the quick-acting science community, industry, and policymakers, the Montreal Protocol was signed in 1987, restricting the production and consumption of CFCs. Every nation on Earth has now signed the Montreal Protocol. So, for the record, your hairspray and aerosol deodorant hasn't been harming ozone since these laws went into effect in the 80s. But why do we still see an ozone hole today? First, CFCs have lifetimes of 50 to 100 plus years, and it will take some time for the concentration of CFCs in the atmosphere to drastically decline. Second, there are still CFCs being released into the atmosphere today. For example, as an old refrigerator or air conditioning unit deteriorates in a landfill, the CFCs within are slowly released. From the time a CFC is released into the air, it takes about 5 years for its impact to be felt over Antarctica, where depletion will occur. The CFCs emitted at the surface eventually rise into the tropical stratosphere. The ozone in the stratosphere blocks most of the sun's UV radiation, so the CFCs have to rise above most of the ozone layer before sunlight can then break them down. Once they get high enough, solar radiation releases the chlorine, most of which eventually goes into ozone-safe forms like hydrochloric acid and chlorine nitrate. When these compounds make their way to Antarctica, those chemical reactions start up. And if you're wondering why Antarctica, these reactions are unique to the polar regions because of their extreme low temperatures and presence of polar stratospheric clouds. One chlorine atom can destroy thousands of ozone molecules, and millions of tons of CFCs were pumped into the atmosphere from the 1920s through the early 1990s. As CFC concentrations in the atmosphere continue to decline, the ozone hole is expected to gradually become less severe, and scientists expect the Antarctic ozone to recover back to healthy levels around the year 2070.
NASA celebrates Women's History Month.
April 16, 1972. Apollo 16, man's fifth lunar landing, sat silently on the pad awaiting its mission. Inside the astronaut quarters, its relaxed crew ate Sunday breakfast. John Young, a veteran of 3 previous space flights, was commander. Ken Mattingly, command module pilot, would conduct orbital experiments around the moon, while Charles Duke explored the lunar surface with Young. April 22nd. Young and Duke would find themselves strapped into a small electric car called the Rover, bouncing across the lunar plateau known as Descartes.
The old water bag is working super. This is going to be a good day, Charlie. Yow! Woo! Man, that was great. Big skid. We're doing 10 clicks, Tony. Covered me with dust on that one.
As Young and Duke rode the bucking rover to the lunar formation called Stone Mountain, NASA geologist Farouk El-Baz wrote on a blackboard on Earth, "There is nothing so far removed from us to be beyond our reach, or so hidden that we cannot discover it." René Descartes. As John Young would later remark, Apollo 16 would certainly help prove that René Descartes was right.
Compacted. Almost like a freshly plowed field that's been rained on.
Yet less than 2 days before, it looked as though this would never happen. It was, in Young's words, a real cliffhanger. The Marshall Space Flight Center team was working on a launch vehicle gyroscope problem that threatened to scrub the mission. Less than an hour before liftoff, their advisory to the Kennedy Space Center launch team was go. The liftoff had been perfect. During the 3-day flight to lunar orbit, the problems encountered had been more annoyances than critical, such as paint flaking off the lunar module, and later a jammed antenna in one of the lunar module's several communication systems. All in all, it had been a quiet flight. April 19th. The burn into lunar orbit was right on.
Hello, Houston. Sweet 16 has arrived. Ryan, this is Houston. How do you read?
The subsequent maneuvers all went without a hitch. Then the next day, April 20th, Young and Duke undocked the lunar module preparatory to landing, leaving Mattingly in the command module.
But we got it done. Roger 5-9, Jim, and we're sailing free. 1, stand by 1, Jim. Okay, we're on time.
The next maneuver was for Mattingly to burn the main engine of his spacecraft to put it into a circular orbit. But as the lunar module emerged from behind the moon...
No, sir. Copy, no, sir.
No, sir. No, sir.
Okay, guys.
No circ. In preparing for the circularization burn, Mattingly had found apparent uncontrolled oscillations in the main engine's backup control system. Following mission rules, he did not make the burn.
How long do you think it's going to take him to get rendezvous, Jerry? I think your estimate of a couple of 3 reds.
With the backup system having trouble, only the primary system was known to be usable on the engine needed to get the astronauts out of lunar orbit and back to Earth. However, the lunar module engines could be used if the 2 spacecraft were docked. The first step in the problem-solving technique: stabilize the situation in the safest manner. Get the 2 spacecraft, which had separated, close enough together to dock if necessary.
As they get them back together, get the things back that they want them, get them mentally prepared to do what they're going to do.
But now, don't take that as an input. I'm talking out loud. I want to say something else I'm sure of.
I don't see any way we can continue on.
At that moment, the chances for a landing looked pretty slim. But you look at a problem step by step. Step 1 underway, you look at step 2. Analyze the problem as completely as possible within the time frame.
We should make sure that that's calm, but there's no way, we don't have any other redundancy or other routes.
And in lunar orbit, Mattingly flew the command module to a rendezvous as Young talked him in.
Okay, fine. Why don't you tell me what to do there, John? Okay.
Word's coming back kind of initially from North American that they're suspecting a rate feedback. Building 45 is Jim McDevitt.
The team was coming up to speed, not only at the Manned Spacecraft Center, but from MIT in Massachusetts to North American in Southern California. Isolate the trouble, simulate it, evaluate it.
You can't use it. If you get a broken wire, you don't know it's going to come back again.
Now like I'm drifting the other way. Not according to my needles. Okay, I'll believe your needles.
Of course, then you would have had no options. Okay? I mean, then it's full speed ahead.
I just don't much see how we can make it on this next trip. I think you guys ought to continue to work.
So you'd only do it if you had a failure on the primary. Well, how would you ever get the damn thing trimmed then? Well, I would. If I had a failure in a primary, I'd shut it down.
Well, we must be going in the right direction then. Yeah, you're going to get there.
Yeah, but I want you guys to go simulate it.
Isolate, simulate, evaluate. The results were coming in. It was beginning to pay off. The simulator tests and other data were showing that with the engine on, the oscillations would do no harm. Despite the earlier pessimism, it was beginning to look pretty good.
Okay, when you come up on AOS, on the next Rev 15, we'll give you a go or no-go for another try.
Manned Spacecraft Center Director, Dr. Christopher C. Kraft, Jr. just came back into the control center after having attended a meeting by management people in one of the back rooms, and the situation is go for landing.
Well, have at it, babe. So we're going to try it. And,
You do have a go for another try here at PDI on Rev 16.
Once more, they would pass behind the moon. And on the next revolution, John Young and Charlie Duke would start their swift descent to the Descartes Plateau.
Okay, filter initialization looks good.
Right on. Feel that beauty? Come on. 200. Pro. Pitch over. Pitch over. Huh? And here it is, Gator, Lone Star. Right on. Call me the thing, Charlie. Okay, 40 degrees, 38 degrees. Right on. On dot, north ray. Okay. Looks like we're going to be able to make it, John. There's not too many blocks up there.
Ryan, you go for landing. Right now looks pretty good.
Go. Go, Hunter. Okay, anywhere to this.
Go, man. Looking good. It looks good.
Flow rate's going down. That comes the shadow. Okay, down at 3, 50 feet. Down at 4. Give me one click up. You're backing up slightly. Okay, 2 down. Stand by for contact. I'm going to let her down. You level off. Let her on down. Okay, 6%. Plenty fat. Contact. Stop. Boom. Wow! Oh, man. Oh, we're running finally here, Houston. Fantastic.
The original plan had called for Young and Duke to get out and explore shortly after landing. However, the near abort had lasted 6 hours. The tired astronauts would sleep. April 21. Mission Commander John Young stepped onto the Descartes formation, 11:58 a.m. Eastern Standard Time.
They are mysterious and unknown Descartes. Island Plains. Apollo 16 is going to change your image.
While their activities were monitored by Mission Control, Young and Duke were also observed by scientists, located across the hall in the Science Support Room. After unloading the rover from its storage bay in the lunar module, they planted the flag.
Hey, John, this is perfect with the LIM and the rover and you and Stone Mountain and the old flag. Come on out here and give me a salute. Big Navy salute. Off the ground, before. There we go. Good.
Young set up an ultraviolet camera to provide the first astronomical observations from the moon. He took pictures of the Earth's upper atmosphere and magnetosphere and their interaction with the solar wind. He also photographed the interstellar gas present throughout space and the ultraviolet halos that appear around galaxies. Astronomers have long wanted a telescope on the moon. Perhaps this experiment would show the moon an ideal base for future astronomical observations.
You want 2 pans?
Yeah, we would like to. John said. I'm not leaning on
Duke drilled a hole into which a heat flow probe was to be placed, part of one of the experiments attached to the station. As Duke drilled, Young set up the central station and the remainder of the experiments. Then, what many considered the biggest disappointment of the mission.
Just some rocks down there in the regolith, Tony. You know, it looks, I bet it's just like the side of that fresh crater we saw back near the limb. Charlie, what? Something happened here. What happened? I don't know. letting it pull loose. Uh-oh. What line is it? That's the heat flow. Pull it off. Kind of sorry. I didn't even know it.
Now that means you've got to mate all those wires, separate wires in there, and have them insulated from one another.
That's right.
And if that doesn't occur, what are the chances of shorting out the central station?
Well, that's another one that they're working.
On Earth, they tried to figure a way to fix the heat flow. On the Moon, the astronauts continued with the other experiments. Young placed a series of sensors in the soil, then fired explosive charges, mapping the lunar subsurface much as geologists on Earth use explosives to search for oil.
4, 3, 2, 1, fire. Stuck in the ground and I try to get this three over there now.
They continued to sample the area and activate the experiments. Then they returned to the rover and prepared for their first trip away from the landing site in search for geological samples.
And here we go.
Their first traverse would take them about 1 kilometer west of the landing site. They would make 2 stops to collect samples and conduct experiments.
You had 10529 in your flight plan.
Well, it couldn't pick a better spot. John, you're just beautiful. That is the most beautiful sight. What's that? You're standing there on the rim of that crater.
This guy, don't really know. You're going to have to use a hand.
Young used a portable instrument to measure the local magnetic field. He would later record the most intense magnetic field ever found on the Moon, far higher than scientists ever suspected.
What's that, Charlie? It's really some crater. As you come around there, there's a rock in the near field on this rim that has some white on the top of it. We'd like you to pick it up as a grab sample. This one right here? That's it. This one right here? That's it. You got it right there.
Okay, we copy that.
There would be one more stop before they got back to the lunar module to close out this EVA. With Duke acting as photographer and Young as driver, they put the rover through a full test.
Man, you are really bouncing. Is he on the ground at all? That's 10 kilometers. Huh? He's got about 2 wheels on the ground. Okay, turn sharp. I have no desire to turn sharp. Okay, here's a Sharpie. Hey, that's great. He's a big rooster tail out of all 4 wheels. And as he turns, he skids, the back end breaks loose just like on snow. Come on back, John. Hey, the DAC is running. Man, I'll tell you, Indy's never seen a driver like this. Okay, when he hits the craters and starts bouncing, it's when he gets his rooster tail. He makes sharp turns.
Then it was back to their lunar base, activate experiments, and close out EVA-1.
Be wise exercise, is that right? Physical fitness, gym level?
Hey, that's right. Please don't take pictures of the hot dogs. Showing the low residue, high protein diet. Anybody got any?
On Earth, the scientists took a break. Tomorrow would be another busy day. April 22nd.
The lunar surface temperature in the sun should be around 135 degrees today.
Today they were headed a little over 4 kilometers south to climb their rover up the side of Stone Mountain.
Man, we are really going up a hill, I'll tell you.
Their first station, a crater 700 feet above their lunar module.
Wow, what a place. What a view, isn't it, John? It's absolutely unreal. really come up here, Tony, it's just spectacular. I have never seen it. All I can say is spectacular, and I know y'all are sick of that word, but my vocabulary is so limited.
Let's see what we can do. If we got that rake soil, if we got certainly something, we could go to one-man sampling and maybe do it.
They would make a total of 6 stops on this traverse, collecting samples from large rocks down through the intermediates to the smallest soil particles. They would operate experiments measuring the strength of local magnetic fields to measuring the resistance of the soil to compaction.
3, 4, 5, 6.
Really gets the detail on top of
Okay, read that again. Get the shadow for scale.
Far away is that crater?
There you go. Hey, we come a long way. Hey, John, it's easier to go straight across. That was fun. I haven't had any trouble. Okay. I have a tough time walking up there.
The sampling time used up, it was time to return to the rover and head back to the lunar module.
And they did it in 2 minutes less travel time than they were
10 minutes
pre-planned. Fantastic.
Tony, how about an extension, you guys? We feeling good. If that all we're going to do tonight was sit around and talk.
But with the limited oxygen and water in the backpacks, it was finally time to close out EVA-2.
Okay.
Now I think they realize that it's not more, a gee whiz, like my friend said, thrill, but it's real exploration, and this is much more serious and much more important for the future of mankind than just a plain exploit, a technical or technological exploit. This is exploration.
Ray Bradbury claims that what mankind sees in the exploration of space is his first chance at immortality since he invented religion.
That about gets it.
April 23rd. The decision had been made not to try and fix the broken heat flow experiment because of the time and complexities involved. Traverse number 3. Today, Young and Duke would head north about 5 kilometers to North Ray Crater, the largest lunar crater to be sampled by men.
Outstanding.
Hey, Tony, it seems to me this is a more subdued surface over here than going towards South Ray. Oh, spectacular. Just spectacular. Wow.
Sorry, Charlie.
Beautiful.
I gotta keep my eye on the driving.
That's great.
Jack, that's a good point to remember. All 3 crews now tend to think they're there before they get there.
I remember.
Man, does this thing have steep walls. They said 60 degrees.
Now, I tell you, I can't see to the bottom of it, and I'm as close to the edge as I'm going to get. That's the truth.
Now the routine, if anything on the moon can be called that. Test, collect, photograph. Keep moving. Time is precious on the moon.
Crater, they look like drill holes is what they look like. You do that in West Texas and you get a rattlesnake. Here you get permanently shattered soil.
How about rolling that one over?
No way.
Then, one of the most spectacular discoveries of the mission.
Look at the size of that biggie. It is a biggie, isn't it?
It may be further away than we think.
No, it's not very far. It was just right beyond you.
And we better press on for the big boulder?
Can't blink here, it's dirty. Okay, we're headed that way. You get the tongs, John?
Yep, we got
I'll carry the rake.
that big black dot.
Fantastic. Like right here.
If we could see to the bottom, we could say for sure if this big black rock is right out of the bottom. But my guess from the old photographs is it probably is.
Okay, that sounds like a good guess.
God, you mean they weren't at it? No. It looked like they were standing right there.
Look at the size of that rock.
I'm curious what they're going to look like when they stand next to it.
We can see. The closer I get to it, the bigger it is. Yeah, but look at the permanent shadowed part, Charlie. On this side over here? Yeah.
And as our crew slowly sinks, we bet upon it disappears into the sunset.
The radius of curvature. Well, Tony, that's your house rock right there. Very good. Don't get too near the edge of that thing. It falls off. Look over at your right. It falls off pretty good. Yeah, I know.
Yeah,
keep going. Can't believe it. I can't either. Okay, let's go on back. I am. Be right with you.
And we encourage you just to look for some variety.
But now it was time to head back to their base and close out the EVA.
All right, we think you could just about head south now.
Yeah, the only reason.
That's it. We're going home again, jiggity jig.
During the previous EVA, a section of a rear fender had come off the rover, causing the astronauts to receive occasional showers of lunar dirt.
And that's a beautiful sight.
Young parked the rover, then moved out to join Duke, enter the lunar module, and prepare for liftoff.
Boy, Houston, the beauty of this place is absolutely incredible.
Smile. FAO. Don't be mad. We'll get it up there. See how nice and leisurely it's been? That's the way it should be, getting ready for ascent.
10 seconds. What a ride, what a ride. Pitchover's on time.
Together in orbit, the two spacecraft pirouetted, each inspecting the other.
This is one of the fastest maneuvers I've made in a long time.
The inspections complete, the command module and lunar module maneuvered to docking. John Young, Ken Mattingly, and Charlie Duke, reunited aboard the command module, settled down for tomorrow's tasks. Jettison the lunar module and burn out of orbit.